Hello, my name is Michael Yankee, and today I'll be discussing the VCD package for R. VCD stands for Visualizing Categorical Data. This is a rather large package with many functions and many data sets. You can see through the list here of everything that is available here. More specifically, there are about 46 functions and 33 data sets. That being said, I will not be discussing each and every one of them. Instead, I will focus on visualizations for categorical data, mostly contingency tables. There may be one or two that pop up in here that compare numeric to categorical, but it will primarily be categorical versus categorical. What we'll do is we will step through code as a way to demonstrate the features that we're going to be looking at. And I should point out that all of the examples that we're going to look at here are pulled from the VCD documentation, perhaps in some cases with some slight modification to either address errors that were in the documentation or to better show a point that I'm trying to make here. So with that, let's get started. So we'll load the VCD package. We'll also load mass. The only reason we're loading mass is that there are several examples that use the Titanic data set. So the first plot that we're going to look at is called the Assoc Plot or association plot, and this compares a contingency table two-way. And what we're going to try and get out of this is, are we seeing higher or lower than expected counts on pairings of the categories in the two variables? So anyway, so we'll load the hair eye color data and take a look at that. And what we see here are two tables, one for male, one for female, that holds hair color versus eye color. So for our plot here, we only want one table. So what we're going to do with the margin table is we're going to combine the two genders together into a single table. We can see that it sums them up by eye versus hair. And Assoc here then will plot that. So we can see on the right hand side in the plot, for example, black-haired, brown-eyed people have a higher count than we might expect in here compared to blonde-haired, brown-eyed people, where fewer than we might expect in a population, where maybe red hair and these other eye colors are closer to normal. Same with brown. I mean, there's some dips. I don't think we'd ever get perfection. What this doesn't tell us here is how significant or strong those deviations are. So what Assoc has is a shade option here. So we will do that. And what we do is we get a scale of color from red to blue. That's for the Pearson residuals. That tells us the strength and also that it's significant. So we look at the blonde-haired, brown-eyed, that it's pretty significantly lower than expected, where, again, that compared to before, the black-haired, brown-eyed people is quite a bit higher than we'd expect for the population. The next plot we'll talk about is the CD plot. CD stands for conditional densities. Essentially what it is a density plot for the numeric variables across the categorical variables, but it's, as you'll see, spread to cover 100% of the plot itself. So let's take a look at arthritis data set. We can see here what the type of data that's coming in. We're going to concern ourselves with the improved value versus the age value. So here's our basic plot. We can see the densities moving from left to right as age increases. Interpretive, like the none improvement is higher when you get to 50 versus the other two categories. It's really thin here. Then as you get older, it seems that the sum improvement increases as you get older. As you'll see as we go through this, sometimes these plots have some issues with being able to show all of the values here. So for example, marked is not present. If I look at the larger version, we can see it here, but Can't always see it within our studio itself. One of the parameters we can pass is BW, which is smoothing bandwidth. So here there's an example from the documentation. We can see that it changes it a little bit. So really what the CD plot is it's applying some smoothing to the values to make it a little bit more readable as opposed to jagged. I can take that and make it 2. We can see this kind of all over the place. They give this other example. I'm not exactly sure what SJ stands for, but it's very similar to the 3. Another example is space shuttle data. What we're looking at here, or we'll be looking at, is failure versus temperature. So there's just 2 yes, no that we're going to look at here. But it's a nice illustration of really easy to see as the temperature increases above 60, the number of failures goes down, and it's almost no failures, when you get above 80 degrees. Another plot that compares numeric versus categorical is the spine plot. And as you see, it's really kind of a set of stacked bar charts that are divided along the numeric. Could be kind of a stacked histogram too, if you want to think of it that way. So we'll look at arthritis again. Here we're going to look at improved versus treatment. So we see again the percentages up to 100%. So with the placebo, there's a big difference between the treated, so there's a lot more none improvement than in the treated group. But if we look at the same variables we looked at before in the CD plot, we can see on the right here, it's not smooth, so it's broken down in, we defined it as 5 groups here. So you can compare those groupings together. It does different, like we can do quantiles to kind of smooth it out a little bit. And we see here there's some other ones where, like, Scott breaks it down into groups by 10. Sturgis is 5s. There's various functions that do this, but then we can now look at age group 20 to 30 that there was, most of them were no improvement. There was some marked compared to 50 to 60. I think you've got the best improvement here. It's pretty easy to see that way, but there's no gradual change. It's rather abrupt. To compare this to the CD plot, we can look at that space shuttle data again. So if we look at here the temperature, you can see it kind of steps up here, and then when you get to that 80 to 90 degrees, there are no failures. And just as a reminder, we can look at that, what it looks like compared to that. So again, there's just smoothing in the CD plot. When we get to this plot, it's not so much smoothing, but they do have to group it together though, so there's still some averaging going on in that regard. Moving back to purely categorical, one of the simpler ones in here is the double-decker plot. And the double-decker plot visualizes several categories across more than 2 variables. So we use the Titanic data set here to demonstrate. Let's take a look at what's in there. And what we can see is several matrices where we're looking at, for example, this is a child, and did they survive, and what was the gender versus what class they were on the Titanic, and adult, survived, no. So there's 4 different large groups into these subgroups. So the double-decker plot will plot all that out so we can see the breakdowns. Actually, if we zoom in on this a little bit, it might be a little bit easier to read. So our main category here on the bottom is which class, first, second, third, or crew. And then we divide that into male versus female. And then age. No, by age, it's just are they a child or an adult. This is where you really need to know your data that's coming in, because there's not enough room to actually label it here. So if we look at first class, male, adult versus child, that child here is really thin. Same for female. And then when you actually look above, did they survive, yes or no? You can't necessarily see here in the sliver whether they survived, then it's really hard to read if there's gray. But by looking at it, I would assess that none of the children here survived in any of these categories. Not until you get to third class do we see a higher component of children and higher survival. So the sizes give you a sense of how much data for that grouping is present. Obviously, children aren't represented in here in any high counts until you get to third class, but obviously in crew you wouldn't have a whole lot of children, and then in first class apparently there isn't a lot of children there either. These other lines here are additional ways that they just generate the same output, but you can define the dependent variable as survived, so that puts it at the top, or you can do it formulaically where you get survived here as your target and then all the other variables and define the data set. But as you can see from the plot on the right, there is no change to the output. Fourfold is a rather interesting plot, I think, as we'll see in a second. Let's load the UC Berkeley admissions data set. We can take a peek at that. We can see that we've got this data set divided by department. And across the top we have male, female, so gender, and then whether they are admitted or not. Then we have this aperm function. And what this does, I made a note for myself here, it does a transposition. And if you look at the output here, you can see that what it really does is it flips the admitted rejected versus the male and female. This is done for the purposes of this demonstration. So we changed some names here for the dimensions and some other things, and we can then take a look at the final table where it's all brought together, so we can see whether males and females were admitted or not based upon these 6 departments at UC Berkeley. So if we look at an example to plot here, we can see that it gives us a 4 squares here, or 4 folds, I guess they're calling it, and we can look at the rate of admissions for females versus males at the top. Again, the coloring here would represent whether they're higher than expected or lower expected in their counts. So we're looking at males. There's a higher than expected yes admitted versus no's, and the reverse for females. What we can also do is I believe we can plot it by each department, so this is a little harder to read. So if we blow it up here, I know it's small, not a lot I can do about it, unfortunately. So here's this department A. Now we see it's a little bit different when we look at department A, where males are actually have a higher rate of non-admission than admission, and reverse for females. So, but then when we look at across the other 6 departments, the coloring is a lot lighter. Obviously, it's not clear, but the rates between male and female are much closer together. So it's really department A that's having the most influence on this. They have this other fiction called a COTAB plot, which we'll look at in a little bit, but it does the same thing, but it's a little bit easier to read. But it gives us the same output, but it's a little cleaner. Anyway. Mosaic is a plotting method that is probably familiar to quite a few people. VCD has an implementation that extends it a little bit. So let's take a look at that. So we'll load Titanic again, just as a reminder of what data that we're looking at, divided by age and whether they survived or not, and their class and their gender. So if we take a look just at the whole data set on a Mosaic, one thing I think you'll start to notice here with the plots that we're showing here is that a lot of them are just different ways to communicate the same thing. So really, it's up to the analyst to decide, which one best communicates what you're trying to get across, or gives you the biggest piece of information. So this looks a lot like the double-decker, where it's still plotting everything across, but it's more horizontal. So we can see crew, third, second, and first, and the breakdown adult and child, and gender is across the top. So, sorry. So what we can do is we can add some shading in here and isolate it to a few of the variables. So if we look here, we can see now that we can see some higher and lower than expected values, and to the degree of which that they occur. So if we look at adults and males, there was a much more unexpected result of them not surviving. Might be interesting to find out why that was. And it's the reverse for females. Perhaps it's chivalry. If we look at another example for the hair and eye color data set, again, a reminder of male versus female, of what we're looking at there. We do hair eye color with shading. Higher than expected, I guess. So if we see female and male here, we see they're both higher than expected. So I would read that to be independent of gender. There's a higher occurrence of black-haired people with brown eyes, which actually, if you remember from the start of this, that was shown in some other plots. And then if we look at blonde, again, independent of male and female, there's lower than expected brown-eyed people in there. What we can do is we can actually, in that shading here in the suspected, we can target which ones we are interested in. So in this case, we're looking at the independence of gender from hair and eye color, and when we're only worried about that, we see a little bit down on the bottom with blonde and blue-eyed that females have a higher occurrence than expected than males have a lower than expected occurrence. Taking a look at another example, we can look at the eye color from, we just flip them around a little bit, we can look at the independence of eye color from hair and gender. Now we see something similar before. Again, for example, black hair and blue eyes, we have lower than expected counts for both male and female. Okay, the sieve plot was a rather interesting one. I had to do a little bit of research on that. It's not one I was familiar with. What it gives us is a little bit more detail into observed versus expected values. So again, with the hair eye color data set, remind you there, what we're going to do is we're going to aggregate it and eliminate gender for this discussion. So here's a first example plot, and so we're telling it only show us the expected values. So the size of the large rectangles or squares are the expected values, the small ones inside are the observed values. So it gives you some way to compare the proportion. What we can do is we can add some shading here, and following that, so we can look down here, for example, hazel eyes and blonde hair. It's telling us that we're seeing a lower than expected number of values, and if we count the squares in here, we got roughly 7, like 10 or so. If we look at hazel and blonde here in the output in hair eye, we can certainly see that it's 10 here, so that's what that's representing. Take another look for the whole complete set. So that gives us an idea of gender and hair and eye color, and the boxes again are the expected values, and we can get an idea from the number of squares the observed values, and are they greater or less than expected. One of the nice features it has here, it'll actually give us counts. So in this case, it's giving us a count of observed values. Looking at that hazel blonde example again, there's 10. Conversely, we can also do the expected values inside the plot, and it gives us a way to compare. So before the hazel, we are observing 10 but expecting 20, so it gives you an idea of how far off we are. Okay, we're actually going to skip struct plot and move to MPlot. The reason we're going to skip that is because it Well, I'll just run through it. It's really just other ways to define plots that we've already looked at. So it's more of an under the hood type of function that it's doubtful that you would call it directly. So we'll move on to MPlot. MPlot is a method to take other types of plots and put them together in a grid so you can see them in one view. So looking at Titanic again, we will look at a mosaic versus an association plot in one single output. So in this one, it's a little hard to read. So here we see the two plots side by side with essentially the same data. We could also set them to variables here and plot them out together here in the same manner. They are essentially the same here, though one is plotting expected and the other one is not. We can also have, here, it's just another example of some different plots. Sieve and this agreement plot, which I didn't discuss because I don't know that I would ever use this agreement plot. It's a little, in my opinion, a little difficult to interpret. Maybe it just requires more study, but not quite sure what it's telling me there. But it's not restricted to 2, so here's an example adding a third plot to that output. And I don't know that there's any limit, but I suppose at some point you would get diminishing returns by trying to fill up this space with more and more plots. You can already tell, and I'm sure you've seen it throughout what I'm showing you here, is that there's some limitations here with the labeling, overlapping, being hard to read, and I've not yet found a mechanism to control the text direction. It doesn't honor any of the type of things that you would see with ggplot or some of the other plotting like par. You can pass it in, and it doesn't honor it when you tell it. So maybe there's something buried in the documentation that I didn't see. Maybe that's something that's going to be added to a future release, but this is less than ideal to read. Anyway, so that is MPlot. Right, and the final piece of plotting that I wanted to look at is this cotab plot. Much like MPlot, it's another one where you can aggregate multiple plots, but these are not of differing types. They're all of the same type. So let's show some examples of that. So using UCB admissions again, here we can do a plot where we're comparing admissions to gender by department. So to the right of the pipe is what's telling us how to divide this plot. So department A through F, and it looks like by default we get a mosaic comparing rejected to admitted. We can change that to an association plot. We see that like we saw earlier, but for all 6 departments. Another thing it gives is you can set up the panel ahead of time and then pass it in as a parameter here. So here we're going to do a co-independence plot, and we're going to make department the conditional variable with an association type, and then we can plot that. So we get the same as pretty much before, but by passing in that conditional variable, we can see that the female in department A shows some differences in expected versus observed. And again, as I said, you can do multiple different kinds. Here's a list of all the different options you can pass to cotab panel. Here's a fourfold. We saw this earlier, which was interesting. Again, a mosaic like we saw, and another example of a sieve plot. So this is actually hard to read, even when you blow it up. So without any coloring, I don't know how useful this is, but it is an option. Perhaps if you have lower counts, it's more useful. So so this can explore some of these other ones here at some point. Okay, so there's just a couple more functions I want to cover that are non-plotting that I thought were interesting. The first one here is the associatstats function, which actually I came across for our project work, and it is immensely useful for comparing two categorical variables for independence, because there's quite a bit of output to interpret, and it's easy to understand and consume once you know what each of the metrics are telling you. So we'll load arthritis again. Then what we're going to do is we're going to create a table that just gives us improved versus treatment. So it's a 2 by 2. We look at the output there. Well, not exactly 2 by 2, 2 by 3, but so let's give us the treatment at the top, whether it was a placebo or they got the treatment, and did they improve, and to what degree. So the associate stats function you can just call directly on that table. You can also pass in variables directly from a data table if you want to. So we see the output here. There are 5 metrics that are coming out here of interest. I'll point out quick first here. So it's important when I said 2 by 2 versus it's actually 2 by 3. This phi coefficient, what you're seeing is NA down here, is only for 2 by 2 variables. So we're getting an NA down here because it's a 2 by 3 or 3 by 2, however you want to look at it. So we've getting two chi-squared outputs here, likelihood ratio and Pearson coefficient. Both are essentially the same. What we're really interested in here are the p-values for these two statistics, and they're both below 0.05, which means it's significant, which means we reject the null hypothesis of independence in this case. Same with these two down here, the contingency coefficient and the Kramer's V. Both of those give us an insight into not only are they associated in some way, but what are the strengths of those associations. So, and they're on a scale from 0 to 1. 1 means they're perfectly associated, 0 they're not associated at all. And we can see in both of these cases, we're seeing values near 0.4, which is a pretty strong association between improved and treatment. So from this I would deduct that these two variables are not independent, and they're actually fairly, not super strong, but fairly strongly associated with each other. Also, the function of you can do a summary on it, which really doesn't give you a whole lot more information. It will give you how many cases are in the table, how many factors are there. It gives you the chi-square, but even though it's repeated, so it's just a little bit more information, but not a ton. Okay, and the last one to look at is table 2D summary. It's a pretty simple function of what it does, but I thought it might be useful in some regard. What it does is it takes a two-way table, and it does some, it just sums up those rows and columns. So we look at UCB emissions again. This is what the data itself looks like. Again, by department. We're going to take this margin table function, and we're going to combine things on the first two columns. So we get admitted versus gender. So what the table 2D summary will do, we'll add those up together. So what we get is totals for the rows on the right, totals for the columns underneath, and then the total for everything. You can see that matches the total number of cases here. It does give you a chi-squared and a p-value when doing that. So, and assuming it's measuring that against this summed up data as opposed to more specifically in the table itself for all the various categories that we summed over. So those are all of the functions I wanted to cover. There's a lot more to learn in this package. There are things that it does with log odds and linear models and those type of things that I didn't really dig into, so I could stay focused. There's some improvements, obviously, that could be done here with how little control you have on how labels are plotted, so you can make it a little bit more readable. The other thing I wanted to mention is that there is also another package which I haven't really looked at yet called VCD Extra, which I believe is an extension to VCD. Yeah, here it says extensions, which gives another large set of functions and data sets that you can apply. Like I said, I have not examined this. I don't know, perhaps in here there are some fixes to the plotting, though probably not. I would assume they would add that to the main package, but this is another area to explore. So thank you.